Okay, let's move on. In the last class, we started with molecular orbital theory, and we saw that there are three criteria that determine the covalent interaction within a molecule. So this is the orbital overlap criterion, that's the energy criterion, and that's the symmetry criterion. At the very end of the last class, we have determined whether the symmetry of orbitals is wrong. All right, for a few examples. So we used the water molecule as an example and looked at whether the interaction of the 1s orbitals of the hydrogen and 2s and 2p orbitals of the oxygen atom in the water molecule lead to right or wrong symmetries. We saw that the decision is not always easy to make, because we need to see by inspection whether the bonding and the anti-bonding interactions cancel out exactly or not. And this decision becomes more difficult as the molecule becomes more complex. So in the following, we will see that when we use group theory, then right and wrong symmetries can be determined easily, and molecular orbital diagrams can be constructed more easily as well. So the method group theory uses in order to determine right and wrong symmetries is called the symmetry-adapted linear combination of atomic orbitals. And the symmetry-adapted linear combination of atomic orbitals method applies a number of steps, a number of rules consecutively that lead you to the decision about right and wrong symmetries in a formal way. And based on that decision, you can then construct molecular orbitals. So what are these rules? So firstly, we need to determine the point group of the molecule from which we want to construct the molecular orbital diagram. So in the next step, we need to define the axes in our coordinate system in a useful manner. So thirdly, we actually have to do then the symmetry-adapted linear combination, and that comprises three steps. We first need to decide, well, what are the ligand atomic orbitals in our molecule, and what is the so-called central atom. So then we combine ligand orbitals to form so-called ligand group orbitals. So these are usually the orbitals in the ligand that are the valence orbitals, and that symmetry operations can interconvert. So these ligand group orbitals, or the number of the ligand group orbitals, must be equal to the number of ligand atomic orbitals from which they have been constructed. So fourthly, you need to determine the symmetry types of these ligand group orbitals, and that requires two steps. You need to determine first the reducible representation of the ligand group orbitals, and then the irreducible representations associated with this, and we will see in a moment how this works. And in the last step, you combine ligand group orbitals and atomic orbitals of the central atom that have the same symmetry type to form molecular orbitals. Okay, so the number of MOs of a particular symmetry type must be equal to the number of ligand group orbitals and atomic orbitals. So with this information, you can then construct the molecular orbital diagram under the consideration of orbital overlap and the energy criterion in addition. At the very end, when you have constructed molecular orbital diagram, it's always useful to check that the number of molecular orbitals are equal to the number of atomic orbitals. If that's not the case, then you must have made a mistake. And in this case, you have to go back and see where the mistake is. It must have been occurred by executing one of these 5 steps. So these are the rules in an abstract form. Now let us apply these rules to an example, and we can just stick with our water molecule. So first we need to determine the point group, and we know that the water molecule belongs to the point group C2e. So next we determine the coordinate system, and we can just use the coordinate system that we used before. So the x-axis can point to the right, and the z-axis can point to the top. So that makes the xz plane the plane of the molecule, and the y-axis stands then perpendicular to the xz plane. So what is to do next? Well, we have to determine what are the ligands and what is the central atom. So that's an easy decision. The central atom will be the oxygen, and the ligand atoms will be the 2 hydrogens. So in the next step, we need to look at the ligands more closely and see what are the valence orbitals the ligand has. So in this case, it's very easy. The hydrogen has only the 1 s orbitals as the valence orbitals. So now we need to combine the ligand orbitals to form ligand group orbitals. So how many ligand orbitals do we have? Well, that's 2. Okay, the 2 1s orbitals of the hydrogen. So we would expect that we have 2 ligand group orbitals that will result from the combination of the 2 1s orbitals here. So this is our first step, and the next step is now to determine what are the symmetry types of these 2 ligand group orbitals. In order to find that out, we first need to determine the reducible representation that is associated with these 2 ligand orbitals. And one can do this using what is called the orbital swapping method. So we go through the symmetry operations step by step and decide if we carry out the symmetry operations, do the wave functions psi1 and psi2 associated with the 2 orbitals swap up their positions or not. Okay, so when the orbitals do not swap up and remain unchanged, then the character in the respective reducible representation for that particular symmetry operation will be +1. When the orbitals are swapped over, then the character will be 0. And by going systematically through all the symmetry operations, we will find all the characters of the reducible representation. So now let us just do this. We first consider the identity E, and we determine, well, do the orbitals psi1 and psi2 get swapped up, change their positions as we carry out the identity operation? The answer is, of course, not. The identity operation never does anything. Therefore, the character in the reducible representation for the identity is 1 + 1 is equal to 2. So each orbital gets the character 1. They're getting added up, and that gives the character 2, overall character 2. So next we can go to the C2 symmetry operation. So we rotate around the z-axis, which stands here. So now in this case, do the orbitals get swapped up or not? The answer is, well, yes, they are getting swapped up because the 2 hydrogen atoms change their position as we carry out that symmetry operation. So for that reason, each of the two orbitals gets a character 0. Okay, now we add up the two characters, and that gives again 0, and that is the character, second character in our reducible representation. So the next symmetry operation is the sigma xc's reflection operation. So the sigma xc mirror plane lies within the plane of the molecule. So as we carry out the symmetry operation, do the orbitals get swapped up or not? Can anybody tell me? You may unmute yourself.
No.
No. Okay, they remain in their position. That's correct. So the orbitals are being unchanged. And well, therefore, each orbital gets the character 1, 1 plus 1, that gives 2, and that's now the third character in our reducible representation, lambda. So last but not least, we still need to consider sigma yz. So sigma yz bisects our water molecule here. So do the orbitals get swapped up now? Can anybody tell me again?
Yes.
Yes, yeah. So they are getting swapped up. Okay, so each of the orbitals get the character 0, and 0 plus 0, well, that gives 0. So now we have found our complete reducible representation. 2, 0, 2, 0. Okay, so before we go to the next step, I wanted to briefly explain what's behind the orbital swapping method. So it's again matrices that are behind the orbital swapping method, and the orbital swapping method is a way to determine the characters on the trace of the transformation matrix that represents the respective symmetry operations that transform the wave function. So we can describe the positions of the two wave functions, psi1 and psi2, by a matrix, psi1 and psi2, that contain these positions. Okay, so now as the symmetry operation is being carried out, well, the positions either change or they don't. Okay, in the case of the identity in sigma xc, they don't. Okay, therefore the final matrix after the symmetry transformation is being carried out is the same as the original one. So if they change, if they're getting swapped over, then well, psi1 will be in the position of psi2 will be in the position of psi1, and psi1 is in the position of psi2. Okay, therefore our final matrix is this form here. So again, we need to find a matrix that, when multiplied with the original matrix, gives the final matrix. Okay. So now for the identity in sigma xc, this is the correct matrix that, when multiplied with the original matrix for the 1s orbital, gives the final matrix for the 1s orbital. And for C2 and sigma yz, this matrix here is the matrix that when multiplied with the 1s orbitals in the original form, give the 1s orbitals in their final form. Okay, so now the characters make up the reducible representations are simply this, the sums of the traces of the matrices. Okay, so in this case, this is these two characters for E and sigma xc, and these two characters for C2 and sigma yz. So in this case, we have 1 plus 1, well, that gives 2, and here it's 0 plus 0, well, that gives 0. And that gives the 4 characters of the reduced representation, 2, 0, 2, 0. Okay, so this is just an explanation of what's behind that orbital swapping method. It's a shortcut behind a more complicated mathematical process. All right, but now let's do the second step. Let's determine the symmetry types of the ligand group orbitals from the reducible representations that we just determined. And in order to do this, you can use a formula from group theory, which is called the reduction formula. And this reduction formula is shown here. So it says that the number of the irreducible representations of a given type, and here we mean a symmetry type, is 1 of the order of the point group times the number of operations in the class for a particular symmetry operation times the character of the reducible representation for the particular symmetry operation times the character of the irreducible representation for a particular symmetry operation. And we then sum up these products over all the symmetry operations that we have. Yeah. So this is what this sum sign means here. Okay, so now let's apply this to our problem that we had before. So our reducible representation was this. And now we have to determine these products here for all the different symmetry operations and then sum up these products. We further have to divide this number by the order of the point group. That will give us the number of irreducible representations of a particular type. So now you see here we have overall 4 types to consider: the type A1, A2, B1, and B2. And we need to go through all of them in order to determine, well, do we have a ligand group orbital with that symmetry type or not? And if we have ligand group orbitals, how many are these? So we can, for instance, start with the symmetry type A1. Okay. So if we start with the symmetry A1, then we have to consider these characters in the irreducible representation here. Okay. So these characters will be these characters here in that formula. So now we have to determine the products for all the 4 symmetry operations that we have. So we can start out with the identity. Okay. Now you see here the result. So there's one ligand group orbital which has the symmetry operation. And how did that number 1 came into being? Well, that's a quarter times 1 times 2 times 1 plus 1 times 0 times 1 plus 1 times 2 times 1 plus 1 times 0 times 1. Okay, let's go through that systematically. So this is the first product here. So we have calculated this product by multiplying the number of operations in the class for the identity, and that's just 1. We have because we have only 1 identity operation times, well, that 2 here, the character for E in the reducible representation. So that's this times, well, this number 1 here, because that's the character of the irreducible representation under E for the irreducible representation of the type A1. Okay, now I've explained the first product. Now what about the second product? So the number of C2 operations, the number of operations in the class is 1. We have only 1 C2 operation to consider. That's the C21. So times, that's 0 here. That's the character of the reducible representation. Times, well, the character of the irreducible representation, and that's now this character here. This is 1. Now we need to do the same for sigma xc. So how many operations do we have in the class? Well, we see that we have only one sigma v operation to consider. So you have to multiply with this number with the character of the reduced representation, which is 2. In that character, we have to multiply with, well, this character here underneath sigma v for a 1. So we have overall 1 times 2 times 1. So last but not least, we have sigma yz to consider also. So what is the number of operations in the class? We have only one sigma v prime operation to consider. So what is the character of the reducible representation? Well, this is this one here. And what is the character of the irreducible representation? Well, this is this one here. Okay. So it's 1 times 0 times 1. Here, 1 times 0 times 1. So now we have to multiply this by a quarter. Why a quarter? Because that's one of the order of the point group. The order of the point group is equal to the number of operations in that point group, and that's 4, because we have 1, 2, 3, 4 operations overall. Okay. So that gives 2, that gives 0, that gives another 2, that gives 0. So we have 4 here. So a quarter times 4, well, that's just 1. So now that means that one of the two ligand group orbitals that we are looking for has the symmetry type A1. So we have to apply the same procedure now to all the other symmetry types as well, A2, B1, and B2. We do this using the same mathematical procedure. I'm not going through this again in detail, but just present you the result here. So for A2, we would find that the number is 0, and that means that we have no ligand group orbital of the symmetry type. For B1, we'll find that we have the result 1. That means that our second ligand group orbital that we're looking for has the symmetry type B1. So the number of B2s must naturally 0, because we already found our two symmetry as our two ligand group orbitals. So that means that our reducible representation is the sum of the A1 of one A1 irreducible representation and one B1 irreducible representation, and that the two ligand group orbitals have A1 and B1 symmetry respectively. Okay, so now how we can again interpret this and understand that the ligand group orbitals have that symmetry type. And actually, in a way, we have considered these ligand group orbitals already previously in our last class when we looked at the interactions between the two p orbitals and the 1s orbitals. We have seen that, well, we can choose our algebraic signs either to be the same, or we can choose them differently. Okay. Now this combination here refers to the ligand group orbital, which has the symmetry type A1, while this combination here represents the ligand group orbital with the symmetry type B1. We can again show that this is the case by applying the symmetry operations to the respective ligand group orbitals. So we can maybe briefly do this. Okay, when we apply EC2, sigma xc, and sigma yz, all 4 of them, yeah, then basically nothing happens to the orbitals, okay? And that refers to an irreducible representation in which all characters are +1. While when we do the C to this combination here, when we apply E in sigma xz, then the orbital remains unchanged. While when we apply C2 in sigma yz, then the algebraic sign of the orbital is getting swapped up. Yeah. So this situation here refers to a character of characters of +1 in the irreducible representation. The swapping up of the algebraic signs refers to a character of -1 in the irreducible representation. So when we look back, yeah, then you see that this exactly refers to B1. Okay, for the identity in sigma V, we have the characters 1, and for C2 and sigma V, we have the characters of -1. Okay, so this is how we can understand that one of our ligand group orbitals has the symmetry B1, and while the other one has the symmetry A1. See, for A1, the characters in the irreducible representation are all +1. So this is just an illustration of the outcome of the group theoretical formalism. Okay? Now, for the construction of the molecular orbital diagrams, you basically do not need to think about what I just told you. All that you need to know is what are the symmetry types of your ligand group orbitals. You actually do not have to worry about how they look like, and you also do not have to prove that ligand group orbitals belong to that particular irreducible representation by inspection, just as we did it before. I just wanted to show you this so that you have a deeper understanding about the group theoretical formalism. Okay. Now we are finished with that part, and our next part will now be the determination of the symmetry types of the central atom orbitals. Okay, so now this is easier than the determination of the symmetry types of the ligand group orbitals, because you do not have to determine reducible and irreducible representations. You can determine symmetry type just by looking into the character table. Okay, so first we need to be clear, though, which orbitals of the oxygen atom we want to use. We'll focus on the valence orbitals here. So the valence orbitals of the oxygen atom are the 2s as well as the 3 p orbitals. So now, what symmetry type would the 2s orbital have? So an s orbital has always the totally symmetric irreducible representation. That's always the one in which all characters are +1. Therefore, the 2s orbital has a 1 symmetry because the A1 symmetry type is associated with characters that are only +1. So what are the symmetry types of the 2p orbitals? That now you can see here in that part of the character table. So we know that a p orbital is a linear function of a coordinate. So the pz orbital is a linear function of the z coordinate. You see that the z coordinate is here, yeah, in the line for the symmetry type A1. Therefore, we know that the 2pz orbital has A1 symmetry as well. So now, what about the px orbital? So you see that the letter X appears here in that line for the symmetry type B1, and therefore we know that the px orbital has B1 symmetry. Finally, we want to look at the 2p orbital. We see the letter Y here in the line for the symmetry type B2, and therefore we know that the py molecule has B2 symmetry. All right. So now we know all the symmetry types of our ligand group orbitals. We also know all the symmetry types of our central atom orbitals. So now we can start to combine orbitals of the same type, same symmetry type, to form molecular orbitals, and that's now the next step. So we can go through all the symmetry types systematically and determine how many molecular orbitals will we have that same symmetry. Okay. Let's start, for instance, with the symmetry type A1. Okay. So on the central atom side, we have determined that the 2s and the 2pz orbital have this symmetry type A1. And we've also determined that the ligand group, there's one ligand group orbital that has that symmetry type A1. Therefore, how many molecular orbitals will we expect? So the number of molecular orbitals always equal to the number of orbitals from which these molecular orbitals have been made. So we make them from 1, 2, 3. Therefore, we will get 3 molecular orbitals of that A1 symmetry type. Now, what's the second step? We can, for instance, look at the symmetry type A2. Here we will find that we neither have central atom orbitals of that symmetry type, nor do we have ligand group orbitals of that symmetry type. And therefore, we will not have any molecular orbitals of that symmetry type. Our third symmetry type is the B1 symmetry type. We previously determined that the 2px orbital has that symmetry type, and that also one ligand group orbital has that symmetry type. So how many do we combine? Well, that's this one and that one, so that's 2. So how many molecular orbitals will we get? Well, also 2. So now what about symmetry type B2? We see that we have the 2py orbital that has that symmetry type, but no ligand group orbital has that symmetry type. And that means now that the 2py orbital does not find a partner. Okay? And that means that it remains non-bonding. So now you can see that the result that we got from the symmetry-adapted linear combination of atomic orbitals matches the result that we got in the last class when we determined right and wrong symmetry combinations by inspection. Remember, we determined that for the 2py orbital, no matter what we did, right, we could not choose the algebraic signs of the 1s orbitals to make them not cancel out. Bonding interactions not cancel out. Therefore, we determined, well, the 2py orbital cannot interact. So you see here again that the group theory gives the same result, but we don't need to determine symmetry by inspection. You only need to go through the group theoretical formulas. Okay. Whereas we saw in the last class that for the 2ps, 2pz, and 2px orbitals, we find combinations with the 1s orbitals to form molecular orbitals. The same we find again here. So the 2s, 2p, and the 2px can interact with the 1s orbitals of the hydrogen atom to make molecular orbitals. Okay. So now we have all the information in hand in order to produce a molecular orbital diagram. So let us go through this step by step. So first, you need to write down an arrow on the left-hand side and label it E. By this, we indicate that we will construct our molecular orbital according to the energy levels of our molecular orbitals. So don't forget that arrow and don't forget that E. So E in this case stands for energy. It's nothing to do with symmetry operation E. So in the next step, we write the central atom on the left side and the ligand atoms on the right side. So in our example of the water molecule, that's O and H respectively. So then you write the valence orbitals of the central atom according to energy. So you will have to write the 2s above that letter O. And you also label that atomic orbital with its respective symmetry type. So in this case, that's a 1. So in addition to the 2s, you also have the 2p's. You write them with the same energy. You can write these 3 lines either, well, really next to each other or on top of each other, minimizing the space in between them. So both ways of writing are okay. Both ways of writing indicate that these orbitals have the same energy. So you also label them with their respective symmetry types, which are A1, B1, and B2 respectively. You do not necessarily have to say which symmetry types belong to which 2p orbital. It's enough to just write the symmetry types below all 3. Okay. Then you also write the ligand group orbitals for the hydrogen in an appropriate position. So we have 2 ligand group orbitals, LGO1 and LGO2. You may want to write the LGO2 in energy somewhat above the LGO1, because remember the LGO2 has a node, the algebraic sign changes. Therefore, it's energetically slightly higher than the LGO1. However, it is also okay to write them at the same energy. Then you neglect basically the energy difference, but the energy difference is very small anyway, and these ligand group orbitals are only mathematical constructions. They actually do not appear in nature, so we only use them in order to construct a molecular diagram. But this way to write is a little bit more accurate than the other one. But none of them is actually a mistake. I will not consider that as a mistake. Okay, so now we can start combining atomic orbitals and ligand group orbitals to form molecular orbitals. And we do the symmetry type by symmetry type. For instance, you can start with the symmetry type A1. And I forgot to say that, of course, you should also write the symmetry labels for the ligand group orbitals. So A1 for the ligand group orbital 1 and B1 for the ligand group orbital 2. Okay, but now we can really combine. So we can first construct the molecular orbitals of the symmetry type A1. We know that we expect 3. So now we have to estimate their energy. Of course, it's possible to calculate quantum mechanically their energy exactly, but we will do only qualitative molecular orbital diagram construction here, in which we just make estimates of expected energies. So based on that, we can only say that when we have 3 molecular orbitals, that one would be expected to be bonding and has an energy which is lower than the energy of the lowest energy orbital from which it has been constructed. So in this case, that would be the 2s orbital. So that means that we'd have to write the 1a1 below the 2s. Okay. Then you know that you will also have an interbonding molecular orbital, and this interbonding molecular orbital should be energetically higher than the highest energy orbital from which it has been constructed. Okay, so in this case, that would be this LG. No, sorry. In this case, this would be this one here. So this is energetically slightly higher than that one, although they are almost the same. So it should be higher than the 2p orbital with the symmetry type A1. Okay, so how much lower and how much higher, we do not know exactly. Okay, we just make a reasonable estimate here based on how strongly the orbits interact according to the orbit overlap criterion and the energy criterion. Okay, so then we will have a third orbital, and that will be an approximately non-bonding orbital by approximation. So it can be slightly bonding, can be slightly interbonding. We do not know this exactly. But its energy will be approximately halfway in between the bonding and the interbonding molecular orbital, and we write it this way in our qualitatively constructed molecular orbital diagram. So we label the symmetry types according to energy. So this one here will be the 1A1, this one here will be the 2A1, and this one here will be the 3A1. So it is customary for to use lowercase letters for molecular orbitals, while we use uppercase letters for atomic orbitals and Nicking group orbitals. So please keep that in mind as well. So last but not least, we connect molecular orbitals, the molecular orbitals, with the atomic orbitals from which they have been constructed from using dotted lines. Okay, so you see that actually here, and I just realized I forgot one line. So there should actually be one line also that connects the 1A1 with the 2p orbital that has the symmetry type A1. So please consider there needs to be an additional line here. But you see that, well, all the three MOs are connected with this A1. So if we add this additional line here, all the MOs are connected with the 2PA1, and all three MOs are being connected with the LGO1 that has the symmetry type A1. Okay. Now we are finished with the A1 symmetry type. So now the next step, let us consider the B1 symmetry type. And we know that, well, we have two orbitals that we can combine to two molecular orbitals. And when we have two molecular orbitals, we know that one needs to be bonding and one needs to be interbonding. Okay. So you see the bonding one here, this is the 1B1, and the interbonding here, which is the 2B1. Okay, so we need to write the 1B1 below the 2P-B1, because that's the B1 atomic orbital, which has the lowest energy, and we need to write this 2B1 above this B1 LGO2. So now you see that this 2B1 here is written energetically above this 3A1. Would we know that by qualitative inspection? The answer is no, we would not know that with absolute certainty, but we may suspect it because the A1 orbitals have an influence from this energetically 1,2s orbital also, while the B orbitals only have influence from the energetically relatively high 2p in LGO2. Okay, therefore, we would suspect that this interbonding 2b1 is energetically higher than that interbonding 3a1. Also, would suspect that this bonding one here would be energetically higher than this bonding one. Okay, but because in bonding nature, it would be energetically lower than this approximately non-bonding 2a1. But strictly spoken, we would not know this with certainty unless we did an exact quantum mechanical calculation. So last but not least, we should interconnect our orbitals with dotted lines, as you can see here. Okay, now what's left to do? Well, we still have to fill in the electrons. Oh no, I forgot one thing. Well, of course, we still have the B2 to P orbital to consider that finds no partner. So we have to write it with exactly the same energy into the molecular orbital diagram. Okay? So in this case, we know the exact energy of our orbital because we know it's not bonding. So this line here must be exactly horizontal. So don't write it any other way. Otherwise, I will really count this as a mistake. Okay. So we only 1b2, so we call it the 1b2. So now really we need to go to the electrons. So we know that the oxygen has 6 valence electrons. So 2 of them must be in the 2s and 4 of them must be in the 2p. So for the hydrogens, each hydrogen atom contains 1 electron. We can write them into the LGOs as shown here. So now we have to fill these electrons into the molecular orbitals according to energy. So we have overall these 6 electrons, but these 2, that gives overall 8 electrons that we have to fill now into the molecular orbitals with the lowest energy. Okay, so that fills this one. It fills the 1b1, and it also fills the 2a1. And finally, even the 1b2. So this one here will be our highest occupied molecular orbital. Okay, the 3a1 will be our lowest unoccupied molecular. So now we are really finished with our molecular orbital diagram, but what's insightful now is to compare the molecular orbital diagram picture of the bonding inside of the water molecule with the simple Lewis dot structure of that molecule, which is actually drawn here. So according to the Lewis dot structure, we have 2 covalent OH bonds, in which we have, well, 2 times 2 is equal to 4 electrons. And we have 2 electron pairs at atoms, at the oxygen atom. So let us see if we can find these electrons also in our molecular orbital diagram. So according to this picture, here we would have 4 bonding electrons. And so in the MO picture, we see that we have also 4 bonding electrons. 2 in this bonding molecular orbital, and another 2 in this bonding molecular orbital. Okay? But you see now also some differences. In the Lewis dot picture, all our 4 electrons appear equivalent, right? While here in the MO picture, they are not appearing equivalent. We would know that these 2 electrons have a lower energy than these 2 electrons, while we could not make the statement based on the simple Lewis dot structure here. You see that the molecular orbital diagram gives us here additional information about the bonding in comparison to the Lewis dot structure. So we further have these 2 electron lone pairs. So these electron lone pairs would be considered non-bonding. And you can see that we have also 2 electron pairs here and here in non-bonding orbitals, whereby this one is only is really strictly non-bonding. It's our 2py orbital, while this one is only approximately non-bonding. And you see again that while these two electron lone pairs here at the oxygen appear exactly equivalent, you see that the associated electrons are actually not exactly equivalent. So this one here is actually, these two here actually have a lower energy in comparison to these two here. You see again that your molecular orbital picture gives you a fine and more detailed understanding of the bonding situation. However, of course, you need to put more effort. Okay, it's very simple to write a Lewis dot structure in comparison to a molecular orbital diagram. So which one you choose depends always on which information you need to get. If it's relatively basic information, such a structure here gives you sufficient information. But if you need more detailed information, you may need to construct a molecular orbital diagram in order to get that information. Okay, then let's stop at this point here. Stop the recording.